Hello everyone, I'm Tingwen from KTH Sweden. Today I'm excited to share our CVPR highlight paper this year. TeFlow enables multi-frame supervision for self-supervised feed-forward SimFlow estimation. Today, data are becoming extremely easy to collect, from video captured by everyday device to large-scale sensor logs collected by autonomously driving fleets. However, dense motion annotation are still expensive and hard to scale. This motivates self-supervised learning, where model can learn directly from unlabeled data. The key question is, how can we obtain supervision? In this work, we focus on LiDAR SimFlow estimation, which predicts the 3D motion of each point between consecutive frames. This red 3D vector visualizes the 3D motion of dynamic points. Normally, the supervision comes from the nearest neighbor correspondence between frames. But if we only look at two frames, consecutive frames, point may disappear due to occlusion or sparse light observation. For example, the second example here, the pedestrian is partially occluded, so the supervision based on two frame might be confused on where is the next point. But if we look across multiple frames, the same outtrend may be visible in other time step, providing a more reliable motion clues. Existing self-supervised method facing a trade-off. Optimization-based method can use long-term multi-frame constraints and achieve high accuracy, but they optimize each scene separately and can take hours or even days. Feed-forward methods are fast and generalized to new scenes, but their supervision is still mainly driven from two conservative frames based on nearest neighbor. As shown on the right, these two frame signal can fluctuate sharply over time. So our goal is to get the best of both worlds, multi-frame supervision, but still in a real-time feed-forward framework. This is overview of TeFlow. The network takes multiple aligned LiDAR frames and predicts inflow in a single forward path. The main challenge is not data network itself, as we solved the temporal efficiency with delta flow before, but how to generate the reliable self-supervision from this frame. For each dynamic cluster, TeFlow builds a pool of motion candidates from multiple time steps, adding with network outputs, and then use voting and aggregation to select temporal consistent motion as supervision targets. So let's step by step. The first step is candidate generation. For each dynamic cluster, we collect two types of candidates come from nearest neighbor correspondent across frame. We keep the top K correspondence with large displacements, as they usually provides clear motion clues for dynamic objects. The internal candidates come from the network output prediction, which act as a stabilizing anchor during training. By combining both, we obtained a diverse candidate pool instead of just a single noise two-frame correspondence. The candidate pools still contains noise hypothesis, so we do not directly average everything. Instead, we ask two questions. The first one is, which candidates agrees with others in direction? This gives the consistent matrix. The second is, which candidates are more reliable? Recent candidates and candidates with clear motion clues get higher weight. In this way, the supervision is decided by a weighted consensus rather than by a single nearest neighbor. So after voting, we find consensus winner and the candidates supported by the most reliable neighbors. But instead of using only a single candidate, we aggregate all candidates and that agree with it, and then this gives a smooth and more stable cluster level supervision target. Finally, we train the network with this dynamic cluster loss from point level and cluster level turn, together with static and geometry consistent loss. Now let's look at about the result. TeFlow achieved a SOTA performance on three real-world benchmark. ArcVerge 2 is achieved around 3.5 centimeter, three-way EP, matching the best optimization-based method, Fluxus, with being 150 times faster. Compared to the strongest feed-forward baseline CFlow Plus, TeFlow reduced the dynamic normalized error by 22%, and we also observed consistent gains on new scenes and Waymo, especially on challenging more dynamic objects such as pedestrian and cyclist. And the ablation confirms where the gains come from. The first increase in the temporal window clearly improved the performance, and 5 frames give the best result. This supports our motivation that multiple frame information can provide more stable supervision. Note we use this same 5-frame setting as the default across all datasets. Without datasets is specific tuning, so you might find better results by tuning it. And second, the full objective performance best. The dynamic cluster loss provides reliable motion supervision. The static loss could prevent false residual motion on background points, and the geometry loss align the warped point cloud with near neighbor's frame. So we also ablaze the design of candidates pool and voting. Using only internal candidate, which is the network prediction, or external candidates, which is come from the top K nearest neighbor, and it's worth them combining both, as shown here. This shows that internal provides stability, and where external provide multiple frame geometry evidence, so both are valuable. Then about voting, removing direction consistent reliable weighting or aggregate also degrades the performance, and confirming that full voting pipeline is needed to produce reliable supervision. To summarize and take away message from TeFlow, first, we enable multi-frame supervision for self-supervised feed-forward SimFlow. Second, we propose a temporal ensembling strategy, including candidate generation, consensus voting, and aggregation to mining reliable supervision from unlabeled data. Third, TeFlow set a new SOTA performance for self-supervised SimFlow. It improves accuracy by up to 33% over feed-forward baselines across 3 real-world dataset. We are achieving performance comparable to leading optimization-based method with 150 times speed up. So thank you for your listening. Our code and benchmark are open source at TeFlow GitHub. You can also find all baseline implementation dataset and evaluation script in Open SimFlow repo. Stay tuned with us about the latest work, SimFlow, which explores a new paradigm for scaling SimFlow with synthetic data. Let's check about it. Thank you.